Welcome back, and this is part 3 that will finish up section 3 of chapter 8 on bonding theories. As we ended in our last video, we were talking about sigma bonds forming single bonds between the nuclei of atoms. And we were approaching our next question. If single bonds are forming from end-to-end overlap of these different types of orbitals, how is it that double and triple bonds get formed? And this is where those unhybridized p orbitals come into play. So to get double and triple bonds, those p orbitals that did not hybridize can overlap with each other, and that's what we're going to look at next. As you can see here, we're going to consider the molecule called ethene. Its formula is C2H4, and its structural diagram would be like you see up here on the right. You've got a double bond between carbons, single bonds to each of those 4 hydrogens. Now, each of these carbon atoms, both the one on the left and the one on the right, are sp2 hybridized. The double bond between the carbons results from side-by-side, not end-to-end, but side-by-side overlap of the non-hybridized p orbitals on these 2 carbons. So it results in a pi bond being formed. Now recall that pi bond is not going to form unless you already have a sigma bond formed in between those 2 carbon atoms from end-to-end overlap between those sp2 orbitals like we see right here. So we do get a sigma bond forming here. We can see that sigma bond in this diagram on the right. You can see here at the center there is a sigma bond between them, and that's from those 2 sp2 orbitals that were pointing at each other. Those overlap to form that sigma bond. Now these p orbitals that are pointing up and down, they can do side-by-side overlap, creating pi bonds above and below the axis between those 2 carbons. And that is your pi bond. So a double bond results from formation of both a sigma bond and a pi bond between the same 2 atoms. We can see the individual orbitals and how they overlap in this left diagram, end-to-end resulting in the sigma, while the side-by-side overlap results in the pi bonding. And if we look at this diagram, we can see the pi bond being formed using those giant sausage-shaped regions to represent the single pi bond that's forming there. We don't really see the sigma bond in this right diagram, but we do know that it's there. We saw it in the left diagram. It's just being masked by the pi bond that's shown here. Now we've been talking about ethene, C2H4, and did you know that ethene is a gaseous hormone that's found in most plants? Tomatoes actually release ethene as they ripen. So a tomato placed in a container with unripe fruit can hasten the ripening process. And often it's convenient to pick and ship fruits and vegetables before they're ripe. So the produce industry uses ethene to control how fast the produce can ripen. Now let's move on to another similar molecule. This one's called ethine. Notice that it has 2 fewer hydrogens. So it's C2H2. If you try to draw a structural formula for it, it's going to turn out like this. The only way that you can get C2H2 to form is to have a triple bond between those carbons. Once again, those central carbon atoms have to hybridize. This time, however, they hybridize with sp hybridization. The triple bond between carbons results from overlap of the 2 p orbitals that did not hybridize on each carbon. Those can overlap between the 2 carbons, forming 2 separate pi bonds. You can see that we'll call those py orbitals overlapping between the 2 carbons on the left, and there's also pz orbitals that can overlap. And if we look on the right side in this diagram, we can see there are 2 sets of pi bonding orbitals shown here, one on top and bottom, one in front and back. There's also a sigma bond that's formed from head-on or end-to-end overlap of those sp hybridized orbitals. So we have a sigma and 2 pi bonds, and when we have that, that gives us a triple bond. It should be easy to see why ethine turns out to be a linear molecule. Each of those central carbon atoms, because there's 2 central atoms here, if we just consider them one at a time, the one on the left, that carbon atom, has a single bond to the hydrogen and a triple bond to that other carbon. So what we have is 2 bonds, a single bond and a triple bond, trying to get as far from each other in 3-dimensional space as possible. There are no unshared pairs, so when 2 things try and get as far apart in space as possible, that's 180 degrees. So the HCC bond angle is 180 degrees. And it would be the same if we considered the carbon on the right. We still get 180 degrees. So it lines up completely in one straight line. Now you might be wondering how trigonal bipyramidal and octahedral shapes come about. Those were a couple of those other shapes that I mentioned as being possible shapes earlier. If you look at the central atom in each of these ball and stick models, you can see on the top one that there are 5 atoms joined to that central atom. And in the bottom picture, there are 6 bonds coming out to other atoms from that central atom. Now the only way to get 5 or 6 identical orbitals is to have 5 or 6 orbitals mixing together. Now, an atom only has a single s and 3 p orbitals at a particular energy level. So any other orbitals, a 5th one or even a 6th one, are going to have to be a different type of orbital. And if you recall, once we get to the 3rd period, it's possible to have d orbitals as well. So what's required is 1 or 2 d orbitals to be included in that hybridization. So there are other orbital hybridizations possible. Instead of just sp3 mixing in a d, we get sp3d, which has 5 orbitals mixed together, which would work really well for that top molecule over there. And sp3d2 says that there's an s, 3 p's, and 2 of the d's mixed together, and that would give us 6 orbitals, which would allow the molecule in the bottom over here to be formed. Now, I hope that this has been helpful in helping you to understand the shapes that molecules can take. You will be doing a lab shortly that involves ball and stick models where you get to create those models and turn them around in your own hands and view them from different angles. And that also should help you to understand this section.